Hi, everyone. So we're going to carry on with the last topic in the course, polymerization. So we're going to use this not just to talk about polymers generally, but also as our example model reaction to do some organic chemistry with. Okay. So first, we have to think about what a polymer is and how it's going to be composed. So polymer really is any material or any kind of chain molecule that is what we get when a lot of small units join up to form one large unit. So you can think of them as almost like cars versus what a train would be. So the polymer is the full train, and they're composed of numerous small monomer units. Okay, so the mer part is just to say it's a unit. Mono is one. Poly, if we're breaking down the word, so many mers, right? Um, in general, how big are we talking? So molar mass of polymers can be enormous. We don't even really talk about it in terms of like grams per mole anymore. Often enough, we'll just use the number of atoms in terms of atomic mass unit, and that can be called Daltons. Pretty much equals an atomic mass unit, but it's kind of rounded into one. So when we talk about polymer mass, we could be talking like usually kilodaltons. So thousands and thousands of atoms. So 25 or 100 or even 1,000 kilodaltons is not uncommon for when we're talking about polymers. So often enough, we're also thinking about chain length and how that polymer is going to grow, or even how many monomer units are in it. And usually, in the ways that the polymers grow, it means that some are going to be. So if we just think about like how many polymers we'll find in the solution, and the length or mass, because they're going to be correlated, obviously. You'll get some that are really high, a few that are really exceptionally low, and there's going to be the most of them will be somewhere in the middle. So we end up with a Gaussian kind of curve here. Um, the better the better synthetic methods will try to make that a sharper curve so that you'll get fewer smaller ones and fewer larger ones, but you're paying a lot more too. And usually what they'll do is do a big synthesis and just filter out the very small and very large using some other kind of physical methods. Um, so yeah, so when we're talking about polymer molecular mass, it's very difficult to say like this is the mass, not anything else. Okay, so when we're looking at the process, of course, let's call that polymerization. Okay, polymerization is the process by which the small organic units, so it's the monomers, are joined into a long polymer. Polymers can be synthetic, so made in a lab or by an industrial process. So think about like polyethylene, polystyrene, half the clothes from the 70s. There's lots of them out there. Or naturally occurring. So there we might look at like proteins are naturally occurring polymers. Same with starches. DNA is a naturally occurring polymer. So there's lots of options there too. Two major types of polymer growth. The two that we're going to talk about in this course anyways, the first one we're going to cover is addition polymerization. That one we're going to cover in this video, and condensation, which we've already touched on briefly in a past one, but we're going to do it a lot more in the next edition. Okay, so let's well, actually, before we dive right into addition, let's mention briefly. So usually, as often as not, there's just one type of monomer that just repeats as long as the chain is. If we get more than one type of monomer, they can be incorporated into a chain in a regular sequence. So we could have, say we have monomer A and monomer B. We could have a polymer chain that these things link A, B, or we could get another type of chain where they go just a bunch of A's in a row, switching into a bunch of B's in a row. Or we could end up even with, say, A, B, E, G, Z, X, just depending on how many polymer or monomer types that we have that can participate in the chain growth. So these are all called copolymers. The first type that we talked about, this would be an alternating copolymer because it's alternating between a couple of different monomers. The second one would be a block copolymer because we have a block of them. And the third type, I don't know that it actually has a name like these other ones, but there you definitely think of something like proteins, okay, where we have a bunch of different types of amino acids that can form in a chain depending on the need, okay? So that would be defined by the DNA. And if you're interested in that, we're gonna do a little bonus sequence of videos on biomolecules that won't be tested, but it'll be there available for you to watch if you're interested. Okay, so now let's talk about addition polymerization. Okay, so addition polymerization is as easy as it sounds. So we're just going to add monomers together, and the total mass or the total amount that we're going to have is just the number of monomers multiplied by the molecular weight of the monomer. So these are usually ones with carbon-carbon double bonds. Okay, so we'll be looking at, say, ethene. We could also do, so if we have a phenyl group on an ethene, this is called styrene. And so you can imagine if we join a bunch of these together, it will be polystyrene. If we join a bunch of ethenes together, that's where we get polyethylene. The L, I think, just makes it a little bit easier to say. We could call it polyethene and be correct as well. Okay, so how are we going to get these? So this, what happens here is this double bond opens up. So when I talk about the double bond opening up, we got two carbons, they're hydrogens. We need to open the double bond, meaning we need to make these two. Actually, let's just erase this double bonds first. And we'll draw them in as two separate electrons. So we know that that's making the bond, but we just want to talk about these two electrons. Okay, so the one bond that's linking the carbons, that will be the, let's say, the sigma bond. That stays the same. This other one, which would have been the pi bond. These two electrons that are making that bond, now instead of participating in the bond, it's going to open up completely. Okay, and instead we're going to have, now we have our carbon, hydrogen, hydrogen, bonded to another carbon with a single bond, with its two hydrogens, and the other electron there. So what's going to make this happen? It's not going to do it on its own. What we need to begin with is an initiator. So this is the initiation step where we've got some molecules, so yeah, often enough a peroxide, but something that's going to provide that unpaired free radical electron to begin with. This is what's going to kick off our process, is that electron right there. So it's going to interact with that electron density that's on the double bond, and it is going to bond into one side of the carbon, encouraging this whole thing to open up and creating the new free radical on the other side of this carbon-carbon bond. So what you can imagine is going to happen is the next step, propagation, where now that we have that free radical on the carbon-carbon bond, the next ethene that it comes across, it's going to do the same thing. Okay, so it's going to form that new bond. with that carbon, the same as it just did, and the process continues on. Okay, and we'll do a few more examples like that. How is this ever going to end if we just have it propagating almost indefinitely? As long as we have monomers in solution for it to keep going, there's nothing stopping this chain from growing. Although eventually, of course, it does, right? So there's two options here. One is that our, let's just start this off. There's our growing carbon chain with the carbon, the free radical on it. So either it's going to meet another initiator molecule with its own free radical, and those are going to form a bond, and then the whole thing stops. Or it can meet another chain. And that's going to provide the other free radical to make a bond and close off both of the chains. So there are our options, and once that happens, there's no more free radical. There's nothing else that's going to encourage that double bond to open up. So that is the termination phase. Okay, so that's how we are going to close off this whole process. And at the end of the day, we've got our polymers, which are no longer alive or growing, and have stopped just at whatever chain length they get. And you can see how this process can create a bunch of different lengths, right? So if this live end of the growing monomer or polymer reaches, say, another initiator molecule, well, it stops right as long as it is. If it finds another growing molecule, then it adds the two lengths together. Okay, so that's the growth phases. What I really want to point out, though, is that even though we're opening up these bonds and changing the double bonds into single bonds, there's no change in the atoms that are involved from the monomer into the polymer. Okay, so if we look back here, and this was our initial ethene that's now in the polymer, or the second one even, it still has 1, 2 carbons and 1, 2, 3, 4 hydrogens, just like what we started off with. Okay, so there's no net gain or loss of atoms between the monomer and the polymer. That's why we call it addition. Okay, we're just adding them up. Okay, so the next page just kind of breaks it down, each of these steps a little bit further. Why we think about peroxides. So peroxides, this bond right here, this oxygen-oxygen bond, is extremely weak. So if we have, say, a bit of light come in, that is often enough to break that bond open, okay? So like this benzoyl peroxide, the peroxide just means that it's an oxygen-oxygen bond there. So we would end up with 2 starting monomers, or starting initiators, I should say, that have this oxygen, and a free radical. So that's stabilized by those 2 oxygens there. But it does have just a single electron looking to make a bond with another electron. So it's going to rob that second electron bond from somewhere. Okay, so how is that going to work? Well, again, we just did it with ethene. We can look at it with styrene instead. So I'm just going to do styrene. Okay, so we've got our organic initiator that was a peroxide, forming our radical bond. Okay, so let's see, we have a styrene that okay, has this double bond in it. Now what's going to happen is that that free radical is now going to want to form a bond onto this source of electron density. So let's draw the bond that it could do, and we're going to donate in 1 electron from the radical and 1 electron from the bond itself. So what happens to the other electron? It's going to have to go and sit on that carbon. Okay, so this whole thing goes to, I'll keep the colors consistent. Now we're going to have R1 through an ether, right? So we have, this is now the carbon that it was bonded to. This is this carbon right here, okay? Going up into the carbon that now has a free radical on it, this guy, and bonded onto the rest of the styrene, right? So this benzene ring, okay? But now we keep that free radical alive so that the next one it sees, here's another styrene, okay? So that free radical is now going to do the same thing that just happened and donate half into this new bond. The other one, again, is going to go sit on this carbon, and the process continues, okay? Not forever, but, you know, for a while, until we end up with a long group of styrene or benzene rings on a chain of, these are getting worse as I draw them because I'm trying to draw it quickly, on a chain, a backbone chain of singly bonded carbons. Okay, and again, we don't lose or gain any atoms as this goes through. So if we had the molar mass of a styrene, so a molar mass of styrene as just one of those, so this thing, so let's put some brackets on this because this is how we would show it a lot lower than that. Okay, oop, I gotta get rid of some of this stuff because I want to show you how we will write this. Actually, I'll do it bigger and we'll just start from scratch. Okay, so if we wanted to write that, showing the whole thing, we would do it as just our benzene ring, going through and bonding onto the next one. And this is going to be the monomeric group in our addition polymer. So this is the repeating unit. And I'll write that down too, because it's important to know what we're talking about when I say the repeating unit. And it's going to repeat n number of times. And the molar weight of this chain is now going to be n times the molar weight of styrene. Because again, we didn't pick up or drop any atoms during this process. So it's just however many units we have of this repeating unit is going to be that multiplied by the molecular weight of just one of them will be the total weight. Okay, that's also the propagation phase. I don't need to go over that again. So chains growing rapidly, yes, because that single free radical on a carbon especially is very unstable. And the alternative is going to be much more stable. So if it comes anywhere near this double bond, that's going to form pretty quickly. So talking like thousands of reactions per second, sure, easily. Chain growth, like we already mentioned, is limited by the amount of the monomer that's in solution. If it runs out, it runs out. If it runs out before it terminates, then we have this live polymer that can still create a longer polymer. We just have to dump in more monomer to it. But more of them are going to find a terminal point, pair with each other, and then they'll call it a day. That will be a dead chain. Yeah, the example of propagation I think we just went through. So this would be this process here. So I don't really need to do it again. Termination, as we mentioned, can just be two activated ends of two separate chains, or it can be two initiators or another initiator starting it up. So if we have, say, R1 through the ether, and we'll keep doing these styrenes. Okay, one more. And of course, these are benzenes, but let's just draw some circles in them. Okay, that has its free radical. And there's another one that is of, you know, any length. It doesn't have to be the same length, obviously. But it also has its free radical. So these two are going to react with each other, forming that new bond, each of them contributing in 1 electron into that new bond formation. So there's no more reactive site. So if we want to show the result of what happens here, these now just become a bond, and we're left with the complete non-living polymer. So this is the completed reaction, and the molecular mass of this whole thing, of course, is going to be just the repeating unit of the chain. We can add in 1 each of these, but honestly, when we're talking about thousands upon thousands, 1 or 2 extra oxygens, or 1 extra, and I think in this case it was a benzene, makes such a small difference in the molecular mass. Often enough, they're just left out of the calculation altogether. Again, remembering that it's also an estimated amount, so we would say the mean molecular weight in a range. Okay, other examples of addition polymers. What have I got on my list? Okay, so polyvinyl chloride, PVC. You would have heard of PVC piping before. So that we're just going to take an ethane, and we'll just say that it's 1-chloroethane, or an ethene, 1-chloroethene. So when these polymerize, we're going to have a backbone chain, and we'll just get chlorine coming off of every other one of these. And that would be your repeating unit. Sorry, that would not be the repeating unit. Your repeating unit would be 2 carbons and a chlorine. So that would be your repeating unit going forward. So that's PVC. Thinking about like PVC pipes, polystyrene we did, Teflon goes by addition polymerization. So this is again an ethene, but now we replace all the hydrogens with fluorine. And you should hopefully be able to predict how this is going to look now. So these, I just want to show, like, if this is the single bond, then it would be, say, each one of these now is the single bond. And we have these new bonds forming from the opening of the second one. Okay, this is the new bond formation. And on each of these, where we would have had hydrogen, now there is fluorine. Okay, and again, we're not picking up or dropping any atoms. Fluorines continue all the way through. That's what makes Teflon so slippery, that all these fluorines are covering it. And you know that it keeps its electron density very close to itself, these fluorines. So really, it's not reactive. It doesn't want to form any kind of intermolecular bonding with anything. It's very happy where it is. Last one, let's talk about like a more water soluble with a more polar molecule. So if we have, let me get this right. This is an OH. Okay, so if we have the carboxylic acid group coming off of, again, this double bonded, just an ethene, right? So this would be bonding across, again, that double bond. So this would be in like that and coming off the bottom. Hopefully you can see how that's going to work out, how this would make sense. And this is a polyacrylate. Okay, so this again, switch to red. So this is our double bond that's going to be opening up, would be right here. And so that made its other bond open into this in and out, okay? So this carbon right here is this carbon right here, and we have our double bonded and singly bonded oxygens. Okay, so yeah, so there's a few other examples. You can certainly find more online, but addition polymerization, that's pretty much all there is to it. We're going to have an initiator that has a free radical. It opens up a double bond. then we get a new carbon-carbon bonding forming through the monomers, and whatever was hanging off of that double bond now becomes the side groups on this long polymer chain. Okay, and that's where we're going to stop it for now. We'll pick it up again soon, talking about the final type of polymerization, really the final topic in the course, condensation polymerization. Okay, as usual, thank you for watching, and I'll see you again really soon.